Okay, we'll get started. Okay, number one, I have to make a big change. I don't know about a big one. Well, I have to reschedule our midterm exam. It was scheduled for 6th week Friday, but then I was informed by the statistics department, kind of basically my boss, that they need to have an important meeting on 6th week Friday. So I actually have to cancel class for Friday of next week, and that was the day of our scheduled midterm, so I'm gonna have to push that to 7th week Monday. Okay, and I apologize. I don't like changing things up on you, but let me just kind of put that in here and make sure you guys take note of that. Okay, so class on November 5th, Friday, November 5th. That's what we have. Class on Friday, November is canceled. The midterm exam is rescheduled to Monday, November 8th. Okay, so let me put that in heading 2. Make sure that's visible. So that's okay. And I know you guys are still waiting on homework 3 to be published. I've just been wrestling with what to put into homework 3 and then homework 4. So I think I'm actually gonna release 2 homework assignments pretty soon, homework 3 and homework 4. And I'll just give you plenty of time to kind of complete both of them. Homework 3 will kind of wrap up that we did a little bit of iteration. And then the textbook actually has some questions to think about regarding ethics and stuff like that, which I thought would be interesting to include. And then homework 4, we've been talking a little bit more of these traditional statistics. And so homework 4 will probably end up being like, you handwrite some math problem answer type things. Okay, so it's going to be quite different, and that will be published. And I know I've been putting off on that. The other thing is I'm going to have you guys sign up for. I'm going to create a schedule. All right, so please sign your group up for a kind of project proposal meeting during week 6. Okay, so link to spreadsheet will appear. Okay. All right, so next week, during week 6, I'll have a spreadsheet with kind of a schedule, and you will put your group in for a basically a 30-minute meeting, 20 to 30-minute meeting. Okay, we'll just do it all on Zoom. Okay, so we'll have the meeting up on Zoom. So just in case I'm home or somewhere. Okay, link to spreadsheet will appear. Meetings are 20 to 30 minutes on Zoom. Okay, and so I'll kind of put a little schedule of when I'm available to meet, and you and your group agree on a time that at least 3 out of the 4 of you, ideally 4 out of 4 will be there, but if for whatever reason you can't get everybody there, okay, I will allow 3 out of 4, but ideally 4 out of 4 to be there. Okay, and let me just talk a little bit before we get into today's lecture, because this project proposal meeting, you will be graded on this thing. I want to kind of make sure that and I started grading this because the first couple times I did it, I did not grade, the project proposal, and it was very clear that students put no effort, that some of the groups, not everybody, but some of the groups put in no effort into the meeting and basically showed up very unprepared, saying, we found 5 different data sets and we don't know what to do. And it was very frustrating, those things. So I want you to come in at least showing that you have looked at data sets, you've thought about some of these things, and you've done it. Okay. Now, grading these types of things, there's always a little bit of a subjective component, and so I've tried to break down the rubric for grading to be as clear as possible so that you can kind of see how you've done. Okay. And so there's kind of four areas upon which you will be graded during this project proposal meeting. I will ask you questions regarding the background of the data. I will ask you questions to explain the variables. I'll kind of check to see what kind of knowledge you have of the subject, and I want to see what your idea is for the scope of the project. Okay, scope of the project being kind of like what kind of relationships, what kind of trends and analysis or modeling are you going to do? Okay, so for example, and any of these things can be graded as good, basic, as in like you've done your job but you didn't do a great job, and then or needs improvement means you didn't do a very good job at it. This okay, and basically if you're somewhere around here, you would lose around 4 points, and if you're over here, you're going to lose around 8 points. Now, if you end up, it's total of 25 points, and if you end up in the needs improvement category for all 4 areas, you know that minus 8 times 4 is minus 32. You end up in the negative zone. Okay. Now we're gonna draw a hard line at 0, so you won't actually go negative. All right, but you got to do better than needs improvement in all of these things. Okay, and so you know, I think it's clear. It says regarding the background of the data. Let's start off with kind of the basic category, right? Students can only explain some of the background of the data, but not all aspects required of good. All right, so let's contrast that to good. It will say students can explain the background of the data in detail. You'll be able to tell me how the data was collected. All right, so ask yourself, right? This data set that I have, that I'm working with, can I explain? You can just ask yourself, can I explain how this data was collected? Can I explain, or do I know when it was collected? Who did the collecting? Was the data self-reported, or was it measured somehow, right? So things like that. You'll know if the observations were obtained via a random sample or not. And you would have done some kind of investigation of the actual data itself regarding kind of looking for missing values or duplicated values. And if that's part of your data, you should have a strategy for how to handle them as well. Okay, and that I would say falls all under handling of the data. Now, if you can't answer all of these things, okay, so let's say you know pretty much everything except you don't know when the data was collected or something, right? Like if you're just missing like one of these things, you know, well, maybe you'll lose like 1 point there or something. So the good category, you could still be in the good category, and you might miss like one point or 2 points. And you know, if you're somewhere in between here and here, maybe you'll like lose 2 or 3 points. And there is a little bit of subjective things, but basically to hit good, you got to check off all of these boxes, right? And as you're working through it, you might realize like, I can't find a data set where I know everything about the background data. And you just kind of have to say, all right, well, we've got to make compromises here. I can't expect 100% because I can't answer all of these things, but this data is interesting to me. And even though might lose a couple points because I don't know all of the details on the background, I still want to continue working with it, okay? Don't let striving for 100% prevent you from pursuing an interesting project, okay? I know you guys all got to UCLA because you strived for 100% in your high school and things like that. But there's just going to be things where you have to do, you have to kind of compromise and accept that, okay, maybe I can still do a pretty good job, even if I can't get everything on here to 100%, okay? And then, if you come in and you just say, oh, yeah, here's a data set I found, and there's some major, and I ask you some questions, and you have no idea, okay? Or if you come in and your data is simulated, and I told you, I want you guys to work with a real data set, none of this simulated data, okay? And you come in and I'm looking through it, and I discover that it's simulated data, that's going to be an automatic, you're in a needs improvement for that category, okay? Again, as we go through the data set, I'm going to, as part of the meeting, I'm going to ask you guys to send me either a link to the data or a copy of the data, and I will go through and I will ask you to basically explain each variable in the data, and within the column, okay, I'm going to ask you, what does this value actually mean, right? So if there's a column, that says, rating, okay? Rating, and the rating score is 8.7. I'm going to ask you, what does that 8.7 mean, okay? And where did that 8.7 come from? Is this an average of scores? If it's an average, what scores are being averaged? Who's providing these ratings? Things like that, right? When you see, like on Amazon, if you see a product with 4.2 stars, that 4.2 stars is the average of submitted ratings. The ratings are submitted from users who purchased the product, but also anybody else who wants to write a review for the product, which could be kind of malicious actors at play. And there's also going to be information regarding how many people submitted and things like that. And so, I want you to be able to explain basically what each value in each column means, right? If you have a column and it's some kind of code, right? And the code says R1, I want to know what R1 means, right? I want to know what these things mean and where these things are coming from. You got to be able to explain each variable, the significance of variable, how the variable is recorded or calculated. Students are able to explain the meaning of individual values in each column. And you should be able to tell me what's considered to be large or small, right? Is a rating of 8.7 good? Okay, and it depends, right? If we're talking about an IMDb movie, a rating of anything over a 9 is considered really good for a movie on IMDb. Even above 8, I would say, is okay. And then again, if you can't do that and you're not quite there, you might be in the basic category. And then it needs improvement. This is kind of a list of basically anything you do here that is quite bad, right? So for example, if you have a categorical variable and it's coded in your data as, category 0, category 1, category 2, but you can't tell me what these codes mean, that's a significant, that's a major error on your part, okay? You should not be working with a data set if you don't understand or don't know what the codes mean, okay? Yeah?
Only one.
Yeah, so if you got like a big data set, right, and you got like 20 columns, and one of these columns you can't explain, just tell me, this column I can't explain, we're not going to touch it, okay?
I was actually jumping ahead to the knowledge of subject. What if only one person in your group has like a really deep understanding?
That's good enough. That's good enough. You just need one person to be an expert, okay? Because that's probably going to be your life. If you go into data science, you probably won't know anything. But if you can get somebody on your team that's an expert on whatever it is, then that's fine, because that person can give you all of the insight and knowledge. And so, yeah, when it comes to student knowledge of the subject, right? All right, and so this is really important. Okay, if only 3 out of 4 people can come, make sure the person who's missing is not the one who's the expert on the subject. Okay, make sure that's a very important person to be there, right? Preferably all 4 of you, okay, or the entire group can attend. But if somebody can't attend, make sure it's not the subject matter expert. Okay, so at least one of the students, okay, has to have kind of deep knowledge of whatever subject we're talking about. Either you have first-hand experience, or you've done kind of extensive reading, or something with it, right? Something where you're okay. So if you're not to put you guys on the spot, but if you're dealing with something like data from Chicago and something, and talking about Chicago neighborhoods, either somebody should be familiar with Chicago neighborhoods and know, like, hey, this is the good neighborhood, this is the neighborhood you want to avoid, or something like that. Somebody needs to have done kind of the research and learned about that, and if or lived in Chicago, so they know from hearsay and stuff like that, right? Because like me, I've grown up in LA my whole life, and so I'm kind of familiar with like which neighborhoods are kind of the ritzy ones, and right? So if you hear like Brentwood and Beverly Hills, I know, like, okay, these are like your $1 million homes, and and then certainly without naming any actual communities, there's other communities where you go, oh yeah, there might be it's not as nice, okay, and that's going to affect any kind of analysis you do with housing, right? You're like, hey, why are these houses so much cheaper? Why are the Airbnb rates so much cheaper, or something like that? I'm also familiar with like where public transit is good and where it's bad and things like that. So, so somebody should be knowledgeable. At least one person needs to be, right? And then if nobody has great knowledge, but you at least have casual exposure, fine, okay? You'll end up in kind of probably the basic category. Right, and then if nobody knows anything, and usually I can ask some basic questions just about the subject, and if you can't answer these satisfactorily, you will be in this needs improvement. And so this is kind of my example where students found the wine data set, and then I would just ask, hey, what's the difference between a Zinfandel or a Cabernet? And I don't know. Well, okay, how can you consider yourself a wine expert? Like, right? Like, what role does acidity play in the quality of wine? Like, do we want high acidity, low acidity, medium acidity, right? And if you have no idea, what good is having these acidity numbers measured in your data set, right? And so, if you just say, hey, there's 2 types of wine, red and white, that's not going to be enough, okay? All right, and then finally, a project scope. Basically, based on your data, what kind of questions are you pursuing? What kind of questions are you going to try to answer? Basically, I want it to be something a little bit more interesting than let's figure out what percentage are in each category. Okay, so if your project scope is, hey, I just want to find out what category has the highest number. That's a little bit too minimal and basic, okay? On the other hand, if you try to say, hey, I want to kind of create a system that's going to predict the stock market, that's a little bit too ambitious, right? No offense, but I don't think you're going to figure that out, okay? You might be interested in finance data, and that's fine if somebody's, has a lot of kind of knowledge on finance and stocks and things like that, that's fine. But trying to predict the stock market, everybody's been trying to do that for the last however many years, and it's complicated, okay? So we have that, okay? Does that kind of make sense? All right, and so I will set up a calendar basically with meetings throughout 6th week. I will kind of put in blocks of my availability, and just put your group name, group number or whatever it is, somewhere in there. Put your things, and that will be that. Okay, it's going to be a Google Sheet, which means anybody can edit anybody, and so the important thing is don't be a jerk and delete someone else's appointment. Okay, if somebody has an appointment, technically because it's a Google Sheet and everybody can edit everything, you know, don't be mean and just delete someone else's appointment. Okay, well, with a classroom this big and a total of nine groups, I think we can be respectful. All right. Oh, okay. Let me give you your first view quiz answer for today. It's the letter B. B as in bear. B as in bear. Okay, so we are still doing hold on, I don't want to view via the browser. So we're still kind of taking an approach to classical statistics, and so just kind of looking at our timeline, we'll probably spend this week and next week spending time in going over classical statistics. And so if you were to take Stats 10, you know, this kind of material would be stretched out over 10 weeks. Okay, and we're just kind of, I'm trying to compress it down into a little under 2 weeks, maybe about 5 lectures of stuff. You know, if you took AP Statistics, this will probably feel like a lot of review, but we're going to try to compress that whole year of AP Stats into maybe 2 weeks of stuff here. Okay, so this is like the highlights and the rapid fire mode. And if I'm going too fast, you interject and say, where is this number coming from? Okay, so we left off, and we talked about on Monday. We talked about our sources of data. We have anecdotal evidence and observational studies and experiments. And I think I saw on Campus Wire people were asking, hey, what's the use of anecdotal evidence? So from a statistical standpoint, again, we don't have tools to deal with anecdotal evidence, okay? But does it mean anecdotal evidence is useless? Okay, I certainly hope not, because your life experience is anecdotal, right? Your entire experience and who you are today hopefully has been shaped by your past, but your past is entirely anecdotal. And so the important thing that you remember, right? So you had a bad experience with this one company in the past, and so you say, all right, well, I'm not going to go back there again, right? You say, you ate at this one restaurant, you got food poisoning, you go, I'd rather not go there again, okay? And that's fine, right? But the important thing with anecdotal evidence is you recognize that your experience is not necessarily the same as everyone else's, right? Your experience is unique to you because of all of the things, your childhood, your upbringing, your background, and all of that has shaped who you are. But as far as the general population, it's different. Okay, but anyway, going back, normal distribution. Normal distribution is a continuous distribution, unimodal and symmetric. Continuous basically just means you can take on decimal values. Infinitely many values exist between 0 and 1. Infinitely many values exist between 0 and 0.1. And the normal distribution is technically able to produce any one of those values. And the normal distribution, this is our density curve. The height of the curve represents the frequency of those values. And so we're saying values near 0 show up very frequently. Let me just scroll up here. Values near 0 show up frequently. Values larger than 0, like 1 or 2, show up less frequently as we slope down, or -1 and -2 show up less frequently. And as we go farther out, like 3 or 4, those show up very infrequently, or -3, -4, those show up very infrequently because the curve is pretty much close to 0. Pretty much close to 0 there. I hope everyone's okay. And because it's a probability distribution, the total area is equal to 1. Okay? The standard normal has mean 0, standard deviation 1. We could just ask, hey, what's the probability that a standard normal variable, which we call z, what's the probability that z is going to be less than 0? Well, if the standard normal distribution is centered at 0, the probability that you end up below 0 is just going to be 50%. There's a 50% chance. 0.5, probability is 0.5 of being below 0, and likewise 0.5 chance of being above 0. Okay? So this is, I'm going through this quickly. I think this is okay with everybody. All right. So you have that. This is called the empirical rule. I don't know if you guys remember these numbers from AP Stats or not. Maybe you never took AP Stats, and that's okay. But basically, the numbers you should remember, 68, 95, 99.7. These are the three numbers you need to remember for the normal distribution. So basically, around 2/3, just a touch over 2/3, are going to have z-scores, or between 1 and -1. So if you're talking about the standard normal distribution, where the mean is 0, each standard deviation is 1. If you go up 1 standard deviation to +1, 1 standard deviation below to -1, you're going to get about 68% between here and here. Okay, if the whole thing shades to 100%, you get about 68% there and there. If you go out to 2 to -2, you get most of the stuff, 95%. Okay, 95% is between 2 and -2. And if you go out to 3 and -3, and let me just kind of zoom in a little bit. So if you go out to 3 and -3, that gets almost everything. You see there's just a tiny little sliver over there, a tiny little sliver over there. You get around 99.7% between 3 and -3. These tiny little slivers here account for 0.3 percentage points, okay? 0.3, so 0.3 of a percentage point, about 3 in 1,000 is would be the area of these tiny little slivers. Otherwise, we've gotten around close to everything, 99.7% in there. All right, so just a quick question, just to check our understanding here. If I've got 68% between 1 and -1, and I said, okay, how much do I have above +1? Approximately, what would you say? Around 16%, right? Because if we got 68% between 1 and -1, outside of 1 and -1, we would have around 32%, and that 32% would be split between those above and those below. So we're going to have around 16% each in the side above 1, 16% below -1. Okay. Sometimes we ask something where it's not just a nice number like 1, 2, or 3, and we say, hey, what proportion has a z less than 0.42? 0.42, okay? So for this is what our picture would look like, where 0 is in the middle, 0.42 is a little bit above 0, and we want to know, hey, what's everything to the left there, okay? This is, we would have to use something called a z-table to look this up, and you would, I guess I need to upload one of these things, but basically, if you took an intro stats course, you probably had to use a table like this, and you would go to the row for 0.42, you'd go to the row 0.4 and the column 02, and you'd get 0.6628, okay? Or maybe you had a TI-83, and you would look up the cumulative z probability, and you would type in 0.42 and things like that. Similarly, we can just use R, and there's a function called p-norm. P-norm, you put in the z-score, and you get your answer here as soon as R boots up. So just a quick check, what would p-norm of 0 produce? So here, let me zoom in a little bit. Okay, so if I do p-norm 0.42, I get 0.66275, which is basically what the table tells us. The table says go to the row 0.4, the column 0.02, This area is 0.6628. The area, if the whole thing is 100%, the area to the left of 0.42 is around 66%. And we can use the computer to also give me 0.6628. Okay? What would happen if I type in p norm 0? What would we get? We would get 0.5, right? Because if I'm just basically drawing a line exactly at 0, and we're going to get 0.5, okay? All right, what would happen if I do p norm of 1? Approximately how much do I get there? P norm of 1, what do we say? Yeah. Yeah, anybody. Yeah, around 1 minus 16%, we would get something around 84%, and that's what we get, okay? We get 0.8413. All right, so this is a very, very precise. It gives you many decimals of precision, okay? The table, the p norm and your z table, once I publish that on CCLE for you guys, this will always give you the area to the left, the area to the left. You want the area to the right, you just do 1 minus, right? So if you want the area to the right of z equal to 1, you do 1 minus that, we get 0.1586. So something around 16%, just a touch less than that, okay? So that's what we have there. So if we said, hey, what's the probability that z is greater than 0.42? We do 1 minus 0.6628. And we do that. Okay, so just very quickly, any of these values, it's quite easy. We just type in p norm negative 1.4, and I get around 8%, 0.0808. P norm of negative 1.04 gives me around 0.14917, 0.1492, something around there. This one says, what's the probability that z is greater than 1.04? So to get the probability that z is greater, I'm going to do 1 minus p norm of 1.04. Okay, and I also get the same answer, 0.14917. Okay, and that's because it's symmetric. The area to the left of negative 1.04 is going to be exactly equal to the area to the right above positive 1.04. Right? So if you think of kind of the diagram, it looks pretty much like this picture, except our lines have been adjusted to be at positive 1.04 and negative 1.04. And we say, how much is over here and how much is over here? These two areas will be equal. We got 14.92%, 0.1492 over here. We're also going to have 0.1492 over here. Okay, and so here are my answers. Same answers as below. Oh, and here's a diagram to show that the area to the left over there is equal to the area to the right over there. If we got a normal distribution, we don't always have to deal with the standard normal, where we have mean 0 and standard deviation 1. We can generalize it so that we have a different mean, a mean of 69.5, standard deviation of 3. We're going to just say the height of adult men in the United States is approximately normal with a mean of 69.5 and a standard deviation of 3. These numbers I've just kind of rounded off to be nice and easy to work with. It's something close to 69.5, it's something close to 3, but it's not exactly that. So using this, we could say what proportion of adult men in the US are shorter than 72 inches? 72 inches is 6 feet. And so we're going to say, hey, what proportion of adult men in the US are shorter than 6 feet tall? We've got if the mean is 69.5 and the standard deviation is 3, how do we answer this question? Well, what we've got to do is we got to change this number 72 into a z-score. A z-score is how far we are from the mean, but expressed in standard deviations. Okay? So if the mean is 69.5, how far away is 72 from 69.5? It's 2.5 inches above the mean. Okay, it's 2.5 inches above the mean. Each standard deviation is 3 inches. So how many standard deviations is that distance? Okay, well 2.5 is a little bit less than 1 full standard deviation. 1 full standard deviation being 3 inches, and our distance is about 2.5 inches. So it's a little bit less than 1 full standard deviation. If we do 2.5 divided by 3, we're going to get a z-score, something around 0.83, 0.833, okay? And I could look this up in the table, and I would say, okay, what's the proportion where z is less than 0.83? And that's around 79, 80%, okay? So we convert our question from what's the probability that someone's height is less than 72 inches? We convert that into z-scores, and that becomes what's the probability that z is less than 0.83? And then we can look that number up in the z table. Do we have any questions about how this worked? And so, again, you know, everything is made very kind of easy in R. In R, you could just say, hey, I want to know the probability of being less than 72 if I specify the mean to be 69.5 and the standard deviation to be 3. In this case, you don't even have to convert to a z-score. I could do p norm. Well, first of all, if I do 72 minus 69.5, I get 2.5, and 2.5 divided by 3, I get 0.833333. And I could just ask, okay, what's p norm of 0.833333, right? And I get 0.79767, right? Or if I don't want to go through the work of figuring out the z-score, I can just say, all right, we're looking at 72. The mean is equal to 69.5. The standard deviation is equal to 3. And R will do the calculations for us, and it gives us the exact same answer as well. Okay, oh, your next view quiz answer is D, D as in dog. D as in dog. D as in dog. Sometimes we work in the opposite direction. We're given a quantile or a percentile. And so let's say you wanted to make a hat accommodate up to the 98th percentile in head circumference, okay? How large does this hat need to go, right? How, like, when you adjust it, how big does it need to fit? So we'll say, again, making up some numbers here. Let's just say the average head circumference is 23 inches, standard deviation of 0.8 inches, okay? 23 inches, standard deviation of around 0.8 inches, okay? How do we figure out what the 98th percentile is, okay? Well, the first thing we need to do is we got to figure out what is, if we were doing this manually, we'd have to figure out what z-score is associated with 0.98. Now we could do this with a table. So we would go through the table, and I would look at all of the areas, and I want to find not z equal to 0.98, but I want to find what number, what area. Okay, so here's a number, 0.9798. That's pretty close to 98%. 0.9798 corresponds to z is 2.05. 2.05 would be the z-score that gives me around 98%. Okay, I can get a more precise number by using not p norm, but q norm. Q norm 0.98, I get something a little bit with more precision. Instead of 2.05, it says it's 2.053749, okay? So it gives me more decimal places of precision. But q norm is kind of the flip side of p norm. So if I do p norm of 1, I get 0.8413, and if I say q norm, these are kind of inverse functions. and I say, hey, Q norm 0.8413, let's do, it gives me back, well, something very close to 1. If I put in that whole number, I would have gotten 1. But basically, I'm asking, hey, what's the z-score that will give me an area of 0.8413? The z-score that would give you an area of 0.8413 is basically 1. Okay. And so P norm and Q norm are kind of inverses. And so we have the z-score that corresponds to the 98th percentile. Basically, we're 2 standard deviations above the mean. So then we say, okay, well, what's the height that corresponds to 2 standard deviations above the mean? Well, if each standard deviation is 0.8, and I'm going 2 standard deviations above the mean, then 2 standard deviations is around 1.6. If I include that 2.05, it becomes 1.64, okay? I'd be 1.64 inches above the mean. If the mean is 23, this puts me up at 24.64 inches, okay? And that would be the 98th percentile. And again, using R, I could just type in the same thing. Q norm 0.98, mean is 23, standard deviation 0.8, and then it does the calculations for me and it spits out 24.643. Okay. I always underestimate how long this is going to take. Okay. So I want to introduce this concept of a sampling distribution. We'll have to get into this on Friday. But so today we introduced the normal distribution. And what we're going to do is on Friday, we're going to look at something called a sampling distribution. And so I'm just kind of skipping ahead a little bit here. The idea is when you take a random sample, and from that random sample, you calculate a mean. And if somebody else takes another random sample and they calculate a mean, the mean of your sample is going to be a little bit different from the mean of your friend's sample. Okay? Even if you're drawing samples from the exact same population, right? So different people could draw samples of, say, 20 people, right? So let's say you got a big population, and I give this classroom, every student in this classroom, I give you the assignment, take a random sample of 20 people from the population. And let's assume you're even capable of taking a random sample, right? We talked about random samples is actually a really hard thing to do, but let's just pretend that you are able to do this, okay? Even if all of you take random samples of the same size from the same population, when you calculate the mean of your sample, you're going to get different values, okay? They're not going to be exactly the same. We would expect them to be kind of close to each other, right? If one person's average is 52 and somebody else's average is 53, that's not all that weird to us, okay? Okay, because we're expecting your samples to be a little bit different, your means to be a little bit different, but kind of similar, right? But if one person's sample is 52 and one person's sample average, the mean of their sample is 52, and someone else comes back with a mean of 290, you'd say, that doesn't sound right, right? Somebody must have done something wrong, okay? Because if our sample average is, 52, and someone else's is 290, that seems just kind of strange. So this is what we want to get into on Friday, all right? Is we want to look at how the sample statistics, that is how, say, the mean of a sample will vary from one sample to another, okay? So if we're dealing with a numeric variable, the statistic we're talking about is the sample mean. We expect the sample mean to be close to, but not necessarily exactly equal to the population mean. And so we could kind of make up a scenario where we say, the population has this distribution, mean of 16, standard deviation of 5, and we're going to draw random samples of 5. If we do that, what kind of sample means will we get, all right? And so just some food for thought here, and then we'll end, okay? If the population has a mean of 16 and a standard deviation of 5, just from the properties of the normal distribution, that means around 95% of your values are going to be between the numbers 6 and 26, right? Because we said around 95% are within 2 standard deviations of the mean. If the mean is 16, each standard deviation is 5, 2 standard deviations above the mean would be 10 above the mean to 26, 2 standard deviations below the mean would be 10 below the mean down to 6, and we would say around 95% of your values are going to be between 6 and 26. 99.7% of your values would be between what? 1 and 31. Okay. And I'm going to take a random sample of 5. Okay, so if I take a random sample of 5, you know, maybe I might get one person at random with a value of 6. But it'll be pretty unusual for all 5 people to have a random value of like 6, right? Okay, but anyway, could we get a mean of like, say, 15? Take 5 random people, could their mean be 15? Yeah, that sounds pretty likely. What about a mean of 13? The average is 16. The average of the population is 16. If I'm drawing 5 random people, do you think I could get a mean of 13? Yeah, okay, that also sounds reasonable, but probably not as often as getting 15. What about a mean of 10? So, average is 16. One standard deviation below 16 is 11. Do you think I can get an average of 5 people where the average is 10? Okay, so the answer is yeah, it's not impossible. But this starts to sound pretty unlikely, okay? What about an average of 8? I'm taking 5 random people. Okay, and now remember, 95% are between 6 and 26, okay? And so, could the mean be as low as 8 of these 5 people, right? And so the answer is it's not impossible, okay? We don't want to say anything's impossible because it's random, but getting an average of 8 is going to be pretty tough to do, right? Because I'm getting 5 values, all right? Sure, one value might be 8, one value might even be 6, okay? But for the average of all 5 to be as low as 8, that seems really, really unlikely. Theoretically, yes, but very unlikely. Could we get a mean of 3? Okay, and again, we don't want to say anything's impossible, okay, because technically it's not impossible, but it seems so unreasonable for this to happen, okay? And so while all of these outcomes are theoretically possible, just intuitively we know that values that are far away from 16 just start to become very unlikely to happen, okay? And so we'll illustrate this. We'll simulate the sampling distribution, and we'll take a look at this on Friday in closer detail here. Okay, last view quiz answer for today is A as an apple. Okay, A as an apple. All right, and again, I'm kind of playing it easy this week regarding, no data camp, and I haven't even given you guys your homework and stuff. But I really do want you guys to work on your projects and identify a good data set and work through that rubric and see if you can kind of answer the questions necessary to, try to get in the good category for most of them. And if you can't get good for all of them, that's okay, all right? I don't want you to say like, oh, because I can't get 100% on the proposal, I don't want to do this project. But take a look at that. That should serve as a guideline for identifying and picking a data set that you should work with. Okay, have a good day, and we will see you guys on Friday.